Dear spectator, welcome to Aerosport Engineering. As the name may suggest, we are an engineering company, or more specifically, we are designing propulsion systems for sport planes. And yes, you might have guessed right, based on my broken English, I am a Norwegian. My name is Ole Ringstad, and I am the CEO of this small company. But luckily, I split the visit with my wife Cecilie Bjørneby, who owns the other half of the company. Now, when the realities are out of the way, I would like to welcome you to this video regarding our V12 aero engine that we started developing way back in 2015. First of all, I have to warn you because this will not be a comedy. This engine that we named ASE-650 Saga is a supercharged 330 SID or 5.4 liter 60-degree V12. It is engineered and designed to work as an aircraft engine, and to be a little bit more specific, it is especially designated for the scaled P-51 Mustangs and Spitfires, where I think a proper V12 is the only choice for propulsion. Today's topic will be the intercooler system. You may question why I'm choosing a specific part or a system instead of reviewing the whole engine. Well, there might be a couple of reasons for that. Number one, I think that by the time I'm done with all the talking, most of you have either left or fallen asleep. And number two, this engine's intercooler system is by far the most demanding components we have had to engineer. We spent several hundred hours and many late nights by the drawing board to reach our goals. In addition, machining the different parts was quite laborious, since some of the parts have shapes that makes them harder to produce. So, to be honest, the intercooler system is probably the part of the engine that we are the most proud of. And this is the reason that we highlight it in this video. Now, first of all, and before I go into the topic, there is especially one guy I want to reach out to and thank for his invaluable help. My very good friend Øystein Lie is a very good engineer and an excellent designer. He has helped us transform our ideas, which often has been simple sketches on a piece of paper, into clever and usable CAD drawings. This project would have been absolutely hopeless without his help. So Øystein, in case you're watching, thank you very much. Okay, let's take a closer look at the topic. As you probably know already, an intercooler cools down heated air that has been compressed by either a turbo or a supercharger. This specific intercooler system that I'm about to show you now is no exception. It is designed to cool the compressed hot air entering the engine's combustion chamber. This complete system, which consists of two plenums, several heat exchangers, a mechanically driven water pump, hoses and a radiator, is especially designed for this engine for several reasons. I will discuss the pros and cons in this system and the different reasons why we choose to go down this path. As mentioned earlier, in this session, my intentions are not to be too detailed regarding the rest of the engine, but I might touch some subjects on the general engine layout during the intercooler overview, just to make it easier to grasp the concept. I will explain the rest of the engine in more detail in another video. Okay, let's get to it. But first, let me throw my jacket and move the camera a little closer to the engine, so that you can get a closer look at what I'm pointing out. Okay, as I mentioned initially, we have manufactured two individual plenums, one for each cylinder bank. For the sake of demonstration, I have removed the plenum on your side, but as you can see, I have mounted the right plenum, but only partially. I will take the top lid off to show you the complete assembly after we have learned how the system is built up. Now, as you can imagine, this plenum mounted on the right side of the engine is feeding air to the cylinder bank on your side, and vice versa. The plenum that is supposed to be mounted on your side, or the left side if you want, is feeding air to the right cylinder bank. They are cross-feeding air into the combustion chambers, where the point is to make sure the intake runners will be as long as possible in an already tight environment. As you can see, the only thing remaining on your side are the intake runners. At the top of each runner, you can maybe spot an O-ring groove, but the O-ring is already installed into the groove. This ensures airtight connections between the runners and the plenum. You can also spot the especially designed fuel rail and also the 6 injectors mounted between the rail and the intake runners, which is feeding fuel into the left cylinder bank. And just as a curiosity, on top of the cylinder head you obviously find the valve cover. Both the left and the right covers are CNC machined from 7075 aluminum alloy. Now, in case you would fancy an extended inverted flight, the valve covers become bottom pans, so to speak. They will quickly get filled up with engine oil, and therefore they also need to be drained. The oil needs to find its way back to the reservoir, which in this case is the oil tank you see here on my left. There's a suction point in middle of each valve cover from about here, where 2 scavenge pump stages, one for each valve cover, are sucking oil and air out of what just became the bottom pans. Okay, enough of that. You have probably already understood that I easily get carried away. Here on my left side, you can see a mechanically driven fuel pump. This fuel pump is driven by the end of one of the engine's camshafts. In addition, there are 2 electrical Valbro fuel pumps feeding fuel to the engine. This mil-spec connecting point is for the engine's left side coil pack. Now, if we take a closer look on the other side, we find a water pump driven by the other camshaft. This water pump is doing nothing but circulating a glycol water-based mixture inside the intercooler system. There is one hose going to each of the plenums, feeding 3 intercooler cores with cold water on each side. We will take a good look at how that is done in a moment, but since these 2 pumps are driven by the camshaft, they run at half the engine speed. Modest, one must say, but it is sufficient for the job. You can also see one of the charge air connecting points on the top cover and one of the tubes that feed air from the supercharger into the plenum. The supercharger sits down below, where filtered air is being drawn through a throttle body mounted in front of the supercharger. At full boost, which in this case gives an absolute pressure of 270 kilopascal or 39.1 psi. The air pressure forced into the plenum, or the boost pressure, is 170 kilopascal or 24.6 psi. With this kind of pressure, the charge air temperature is reaching a quite unhealthy 157 degrees Celsius or 314 degrees Fahrenheit, So one understands right away that cooling of the charge air is extremely important. Now, I think that we are done here by the engine for a while. I will take you back as soon as I have explained what is hiding inside one of these plenums. So, come on, let's move over to the workbench so that we can take a closer look inside. What you see here is a complete intercooler unit for one side of the engine, but obviously disassembled. And no, there aren't that many parts to make a complete unit like this. But compared to a traditional air-to-air intercooler installation in a modern car, this unit is a little more complex. Since the intercooler system is based on a liquid-to-air type of heat transfer, one needs to take a closer look at how to design the system to make it fit and work in an already tight environment. It requires quite a bit more thoroughness while you are on the drawing board, so to speak. But first, let me explain my abbreviation liquid-to-air type of heat transfer. What I mean with that is that the charge air coming into the plenum will be cooled by a liquid. In this case, as already mentioned, a mixture of cold water and glycol that flows through the heat exchangers to keep them cold. The hot charge air is then forced over and through the cooling fins of the heat exchanger to cool it down. In this system, this is what the bare heat core looks like. In a traditional intercooler setup, for example, in a modern car, one would normally use ambient air to flow over a radiator, while the hot charge air is flowing through the inside of the radiator or heat exchanger. The hot charge air on the inside will then be cooled off by the cooler ambient air flowing over the outside of the radiator. Of course, you knew about all this. Now, let's take a look at this particular exchanger. This one consists of two different core lengths. This so that we can make a core that fits the maximum length that we have room for in this engine. As you may see, this is a tube made of aluminum, and it has several thousand thin fins, also made of aluminum, stacked tightly together after each other throughout the whole core. Well, except for the joint then, obviously. Each fin is getting cooled off by the cold mixture of water and glycol flowing through on the inside of the tube. The hot charge air is forced over the whole length of the tube, down and between each cooling fin, which again makes the heated fins exchange its heat to the colder water on the inside of the tube. The mechanical cooling pump, driven by one of the camshafts that we saw earlier, is then pumping the water that now has been warmed up by the hot charge air down and into a radiator mounted in the aircraft's belly scoop. Ambient air flowing through the radiator with high speed makes the warmer water cool off to near the outside air temperature. In other words, heat exchanging. And then there is this funny looking tube which is surrounding the core when installed into the plenum. At first glance, one may wonder, this must be in the point where the engineer fell asleep, right? It just looks like a huge restrictor for the air to flow by. You're probably thinking that the core itself, without the shield around, looks like a big restriction. This is a very interesting topic, so let's take a closer look at what's going on here. First, let's imagine these three cores inside the plenum without the tube or the shield around them, because the tube will actually act like a shield. The shield will prevent air from finding the short way through the cores and to the underside of the plenum. The shorter way is obviously here between the cores, and the pressure will also be at the lowest at this point between here. In other words, this is the easiest passage for the air in terms of distance and pressure. So what does that mean? Well, without the shield, the air will not have time to cool down on its way through the cores. This means that without the shield, you will have inadequate heat transfer. A shorter distance and a shorter time span for the air to be in contact with the cooling fins will reduce heat transfer to the cold water passing on the inside of the core by a lot. When the shield is installed around the heat exchanger core, the pressurized hot air is forced through most of the circumference of the heat exchanger, which makes the hot air stay in full contact with the cooler fins in the core, and also for a longer period of time. And this really helps increasing heat transfer. So the shield or the tube is a quite important feature for effective heat transfer in this system. As you can see, there is one water tank in each end of the air plenum. Both of the tanks are holding the exchanger cores in a fixed position. There are 3 cores in each plenum. The water is pumped into the inlet tank, and from there on into the plenums and through the heat exchanger cores. The water is then directed out from the cores and plenums and into the receiver end tank, and from there into this collector tank. The water, which is now warmed up by the charge air, is now directed back into the first radiator in the belly scoop to cool off to ambient temperature. Now, let's move over to the engine again, so that we can take a look at the assembled intake plenum with the intercooler cores installed. Okay, the only part that I have removed from this intercooler plenum is the top lid. By the way, as you understand, this side is feeding air into the left cylinder bank, as we have already talked about. Now, what you may see here is the water hose, the water inlet hose mounted onto the inlet water tank. The water which is led into the tank is let out through 3 outlet ports, one for each cooler core, which makes sure that all of the 3 cooler cores are fed evenly with water. You may also be able to see that the cores are placed tightly together inside the plenum. The shields are actually touching each other, and to ensure that the pressurized air inside the upper part of the plenum will not escape to the underside of the plenum, a thin string with silicone is or will be applied between the shields. This ensures that all the hot air is forced through the cooler cores and cooled down on its way through. When the water, which is now warmed up by the hot charge air, reaches the end tank here on the opposite side, it enters the collector tank and from there is directed down to the radiator to be cooled off. You are probably wondering how efficient this system is and what the benefits are. And I am impressed if you are still with me. And if you are, you have most likely seen some of the disadvantages already. I will come back to that later on. Well, as most of you know from before, water stores a lot more energy than air will do. We can benefit from that through the design of this system and with the type of cooling cores that we have chosen. Because of the design of the aircraft we are dealing with, using water and glycol as a cooling media is the only way we can solve cooling the charge air. More specifically, we have very limited space to route sufficient size tubes in the case we would feed cold air into the engine, through the aircraft, back down into the belly scoop, into the radiator, and then back to the engine. The slick design of the World War II Mustangs and Spitfire fuselage does not allow for this kind of plumbing. Routing water tubes is a lot easier because the size of the tubes can be kept a lot smaller in diameter because of the higher energy of the water, compared to the huge amount of ambient air needed to do the same cooling. So the major reason that we have chosen this type of intercooling is due to the limited space available in the airplane's fuselage. When it comes to how efficient this system is, we really don't have a complete answer to that yet. Or in other words, we don't have any good outdoor testing data so far. We have, of course, collected data from several days with tuning and testing in the dyno cell, but we suspect that this is just an indication of what to expect later on. To give an idea of how the cores are performing, here is one example from the dyno room. But first, let me explain some necessary details during the dyno sessions. First of all, during the test, all three radiators, intercooler, oil cooler, and of course the main engine radiator, were submerged into water in an especially designed tub. This so that we could control cooling temperature by adding cold water to the tub when needed. We tried to average the temperature in the tub while the engine was running to around 20 degrees Celsius or 68 degrees Fahrenheit. This to simulate a typical Norwegian summer outdoor temperature. What we could not control to the same degree was the air exchange rate and the temperature inside the dyno cell. You know, when running the engine at heavy loads and high RPMs from 5 to 15 minutes or more, the dyno room became very hot. The air also got slightly contaminated with exhaust fumes due to the lack of proper ventilation. The temperatures inside the dyno room reached 45 degrees Celsius or 113 degrees Fahrenheit, which is not representative at all for our latitudes. So, most likely, the intake air temperature would affect the charge air temperature while running at high RPM and full boost. Anyhow, to give an example of the cooler core effectiveness, let's take a look at a log from one of the Motec ECUs for a specific run. We measured the charge air right after the supercharger, before the air is forced into the intercoolers. And as stated earlier in this video, we measured 157 degrees Celsius or 314 degrees Fahrenheit. You can see that in the middle row on the sheet from the green line named intercooler temperature, all the way over to the yellow vertical line. After the charge air has run through the intercoolers, or on the colder side, just before the air is forced into the combustion chamber, we measured 53 degrees Celsius or 128 degrees Fahrenheit. The orange line in the same row, called inlet air temperature, will give you this information. That is a reduction of 104 degrees Celsius or 219 degrees Fahrenheit, which is quite a drop and gives us great confidence in the ability to cool down the charge air in our system. Now, I also know that many of you would be very interested in knowing about the pressure drop that we have in this system. As you may know, an intercooler core will give some restriction. Engine builders are always searching for the best core with the least amount of restriction in it. And strangely enough, there is always a better core showing up just after you are done with the implementation of the one you first got. In our system, we did not have many choices. The Laminova course is designed to fit inside tight spaces, and it can go at the expense of other things, like for example, pressure drop. You may see from the graph we are getting the most out of this system. This since the pressure drop starts to increase towards reaching maximum engine RPM, which is set to 5,000 for our engine. If you look in the second row from the top of the sheet, you will find a red line named turbocharger bank 1 pressure, which indicates the compressed air straight out of the supercharger before cooling. The purple line named inlet manifold pressure, representing the cooled down charge air. First, and it's a little hard to spot right away, but where I have the cursor at 4,000 RPM, the pressure drop is 8 kilopascal or 1.16 psi. At 5,000 RPM, where the yellow line, the yellow vertical line, is intercepting the red line or the turbocharger bank 1 pressure, the absolute pressure is 270 kilopascal or 39.16 psi. Now, just to clarify, when I am referring to absolute pressure, this is not the boost pressure, but the ambient or the pressure that surrounds us and the boost pressure together. To calculate the boost pressure, one needs to subtract the ambient pressure from the absolute pressure. Then, when we know that the ambient pressure at sea level is approximately 101 kilopascal or 14.6 psi, and subtract that from 270 kilopascal or 39.16 psi, this gives us a boost pressure of 169 kilopascal or 24.51 psi. To use a more common terminology for aviators, our MAP or manifold absolute pressure would then read 73 inches. Whoa! This is the reading you will get after the charge air has run through the cooler course. The absolute pressure is reduced to 251.8 kilopascal or 36.52 psi, which gives a pressure drop of 18.1 kilopascal or 2.62 psi. Anyone who has struggled with intercoolers and pressure drops through such units knows that this is a little too much. But that is how it is for this installation. This is not a huge drop, we just know that we are approaching the flow limit through this specific cooler course when approaching up against the top of our RPM range. A portion of this pressure drop could be to the fact that the cooler air underneath the heat exchanger course is denser and takes up less space than the hot air above or in front of the heat exchanger course. I don't want to speculate on how much this amounts to or if it is measurable at all, but I would still like to give it a thought. In other words, I am not sure that the 2.62 psi in pressure drop is representing only the restriction through the exchanger course, but also the fact that the air is less dense when cooled down, which again results in pressure drop. Please be our guest to give a comment if you know anything about this topic. For instance, I believe that a good friend of mine, Mr. Jack Kane, has a comment or two he would like to share with us. As a curiosity, I can mention that the water running through the intercooler course was warmed up by the charge air from 20 degrees Celsius to 68 degrees Fahrenheit to 59.6 degrees Celsius or 139.3 Fahrenheit. Also, the particular dyno run took 25 seconds, we measured injector opening time to 79.4% at 5,000 RPM, burning 4.8 liters or 1.26 US gallons of 100 low lead fuel per minute, producing 675 horsepower with a lambda value of 0.78. I know that's a lot of numbers to grasp right away, but please stop the video and take a closer look at the log to see what is going on. Well, I think that we are getting towards the end of this presentation. Let me do a quick summary of this discussion before I say goodbye to you. I promised to say something about the pros and cons. And as everyone understands, there will always be a little of both. I can tell you right away, this is not the easiest way to cool down your charge air. It has been a lot of work, actually a lot more than it needed to be. And yes, you are right, of course, it could have been solved differently. There are many ways to a proper intercooler design. Also, as some of you can see, this complete system does not come free of charge either. But nothing does. Despite the fact that we have had a lot of work with this, and that the economical aspect, designing and manufacturing this system, definitely have passed the boundary line over to the con side, it is worth the trouble. Its slim and narrow design really takes up little space underneath the cowling. As you probably have noticed in this video, this is space we need for other engine-related equipment. Despite some pressure drop at full throttle, this system is very efficient in cooling the charge air because of the innovative Laminova cores, together with the high energy of glycol and water as a cooling media. Also, the very important fact that intercooling could not have been achieved unless we could have reduced the size of the tubes and hoses that go through the airframe. The design of the system gives a very short distance for the cold charge air into the combustion chamber, which again gives less time and distance to get warmed up by the hot surrounding engine parts. And last, but not the least, it follows the curvature of the cowling and looks quite nice, doesn't it? We are looking forward to start testing outdoors, which is going to happen sometimes in the fall of 2021. I don't want to promise too much, but I have a feeling I can unveil something you have never been witnessing before. Without revealing too much, I will try to show you how we are testing aero engines in Norway. Or to a bit more precise, the farmer's way on how to do it. So let's see what is going to happen. And until then, I wish all of you the very best. Your smile is so wonderful. The star in your eyes today, it shines like I never seen before. It shines.